Hi, welcome to this project of building a linear power supply. I had to build one for my fans that I put in my amplifiers for cooling. And since I'm not a professional electronics man, I'm just an enthusiast who likes to build things on his own. I started designing and building a linear power supply. Of course, you can buy ready ones off the shelf, and most probably they will be cheaper. But I just wanted to see if I could build one for myself. So maybe you will think that a novice approach to the whole thing will help you as well. So in the first step, where I started was, of course, researching the net, how to make one, and I ended up that I needed a really simple one, fixed one, 12-volt fixed one. So I put a pen and paper and starting to see what I needed. So I ended up that I needed one terminal connector. So the wires from the transformer will attach. One small filter capacitor to filter any noise from the network. I decided to use a bridge rectifier. Of course, you can use 4 diodes, but I decided to use a bridge rectifier also for space concerns, to rectify the AC to DC. And then I needed some filter caps, of course. I decided to put 2 filter caps. There is a formula, of course, you can use to decide what the minimum capacitance of the filter caps is. One small tantalum capacitor for noise reduction. Tantalum capacitors are polarized as well. Of course, my voltage regulator. I decided to be a TO220, which are the easiest ones to deal with and cheaper ones. Two output capacitors. Why not? I had some laying around, so why not use them? And again, one noise tantalum capacitor at the end, and another terminal connector. For the output wires. So basically this is my plus, this is my minus. So basically what I needed was this here. And this is the ground. The sketch is very artistic. Sorry for this. it helps me to understand the circuit better. So this is the simplest one. So I had all this and I moved to KiCAD. Now KiCAD is a free software and the easiest one. I couldn't afford any professional design software, so I use KiCAD, which it takes some learning to do. Of course, I've never used it before. But I went onto the website. I saw various tutorials, and it's not really difficult to work. You need to just put some effort in it and learn it. So we are in a schematic editor of KiCAD. Again, I am not an expert in KiCAD. I only use it just to design linear supplies. I went through very many versions until I get what I wanted. As I said, we need to put some effort in it. So in KiCAD we have the symbols. So the library, I also want to say that I have installed the DigiKey library. This is where I get most of my parts, so I wanted to have the DigiKey library as well, because the built-in doesn't have everything. So I would start with the terminals, and of course now I know it, and which terminal I want. It's from the DigiKey library. Terminal blocks to wire board. I wanted a block with wires again. So terminal block, two side end, 5.8mm pitch for PCB. And I put it one here and one here. Just to rotate it there, and if you press R on the keyboard, it rotates in the it rotates the component on your orientation that you like. So the next thing is a capacitor, filter capacitor. So instead of searching here, I write over the filter capacitor. So it's just an unpolarized capacitor. I place it here. Then what we need, according to the to our sketch, is a bridge rectifier. So here you can find it on diode bridge. Now the way you are going to go in this sequence is you put whatever symbol you need, but then maybe what you chose is not available for you to buy, so you will have to go back, see what components are available from your favorite source, and then you will have to come back on the schematic and change it. Now I'm showing you what I chose. And of course, for me, I went back and forth several times in order to finalize what the actual component was. I chose this bridge, which is 400 volt, 8 amp bridge, so it will be more than enough for my project. Then after the bridge we need smoothing capacitors. Right capacitor again, and we need polarized capacitors. One, and another one. After that we need a tantalum capacitor which is polarized, so three of them, and then we need our according to our sketch we need our voltage regulator. So again, you need to go back and forth and see what is available for you. I finalized on LM1085 12 volt voltage regulator. It's the simplest one. That's the input, that's the output, and the third one is the ground. So I have my voltage regulator, and then I need 3 more polarized capacitors. What I forgot to mention, everybody and the schematics and everybody always recommend that we put a diode to protect the voltage regulator. So let's add the diode as well. Thousand volts, 1 amp general diode. It's more than enough, and we place it there. So now that we have our components, we start to connect them together. Add the wire. We have here, let's add the wire, and we're going to add the wire here, and the just to make it easier, I moved okay. So we have our you can click and place the captions wherever you like it. This one is not. Okay. So okay, schematic is not that. I can move this here. Very good. I can place this here and I can place this here. So from this to this, and from here to here, and from here to here. So let's connect the rest of the components. Very good. Because I'm a visual guy, this doesn't need to be done. But I just need to do it just so I can see. Come on. So this is sorry, forgot to add my protection diet. So basically this is our linear power supply. This is where we will connect our transformer. This is where we will get our DC from here. So of course it cannot be designed without errors. The bridge is completely wrong, so let's fix it. This one. So the bridge is like this, and of course the plus side is on number 3 pin. And the negative is on number 2. positive voltage is from from number 1 pin to go to the capacitor, and our negative is, let's make it a bit more obvious. Come on. There. What is this? That's it. So now it makes more sense. This is the plus side on pin 3, that's the negative on pin 2, and that's our ground. So let's put some ground. Earth, ground, whatever you want to call it. This is ground, this is earth, let's use earth. So this is it. So finally our design makes some sense. So let's we need to annotate and give all the symbols and numerical numbers. So let's go here and no, reference designators, annotate, and automatically gives the capacitors, the diodes, and everything gives a name. Alright, now we can go and change any of those. These ones I don't need to change, but this C2 I can make it whatever capacitance I want. There's a formula for the capacitance. For a 12 volt linear power supply is around 4,200 microfarad, but I had more capacitors, so more capacitor means more smoothing. So I already had 5,600. So I name this. You can name them whatever you want. By pressing R, you rotate. This is a 10 microfarad tantalum capacitor. This one already here, this one is already there. I had 470 microfarad capacitors for the output capacitors. And the last one is 1 microfarad standalone capacity. So, having finished that, let's try our electrical rules check to see what we've done. And of course we have one input power pin not driven by any output power pins. I haven't designated. One good trick about to remove this error message is to go and set a power flag. If we go to power here, and we can, where is it? We can insert a power flag here and another power flag here. Let's see now if let's make the electrical checks. Yes, of course, it still is. So let's clear these things. Now it's in place. Now it's in place. And our electrical rule check is perfect. 0 errors, 0 warnings. So it means that our sketch is complete. All we have to do is save. I'll just save it as test. Let's replace, and this is the first part. So now we have to go and assign footprints if we want to make the PCB and order the PCB. Sorry, forgot. I forgot to mention that, okay, yes, we have a nice PCB, but how do we attach it to our chassis or anywhere? So, at least on mine, I decided to place some holes. You will find the holes on the mechanical here, mounting hole pad with connection. I wanted to make a connection to ground, so I'm placing 4 mounting holes. And I am connected them to ground. So now I have 4 holes for my PCB, so I can mount it. And also I forgot one heatsink, again on the mechanical. I need one heatsink. It doesn't really matter. One heatsink there. We will assign footprints later on the assigning footprint. So this completes the design of the of our power supply. Okay, now we arrived at the part where we need to decide the components. Yes, I placed this because I already know from my when I did it, I know the components, but this is where you need to decide which components, because when we are going to assign a footprint, and the footprint is what will help us build and design the PCB, this is where we need to decide how big the capacitor, what's the lead spacing, and all the rest. So we have here one capacitor. What capacitor is this? It's an SMD. Of course, it's not an SMD, it's a through-hole. This is what I forgot to say. My linear power supply is a through-hole power supply. It's not a surface-mounted component. Okay, it's an old-fashioned through-hole with electrolytic capacitors. Okay, this is my decision. I do not have the eyesight or the expertise to solder SMD components, and I don't have a microscope. SMD components are extremely small, and I don't have the skills or the eyesight to do this. So for me, it was a one-way through-hole design for the PCB. So we have here the footprint assignment. Let's start with the easy one, with the voltage regulator. You press it, I know, and of course you can go, if you go to the, let's go to the site. So we have, this is what we choose. So LM105IT12. It's in stock. Actually, this time, January 3rd, there's only two 12-volt linear power regulator, voltage regulators in DigiKey. This one is 4.3 euros. This one's 2.3 euros. So I chose the most less expensive, most less expensive, very nice, the least expensive. So it's a TO 223 package. So if we go back to KiCAD, we have a TO package, TO SOT TO23 vertical. So then double click and we assign the footprint. The mounting hole pad is a 3.2 millimeter M3 pad with via. With via. Mounting hole 3.2 millimeter M3 pad with via. The same for this one, and this one, and this one. The heat sink is a Fisher SK104 35.3 to drill 3.5 millimeter M3 screw. Again, this is what I chose. You have to go to your favorite site. I use DigiKey. Find the component, find the component, check the data sheet. Go here, check the data sheet, whatever the component is, okay, and it will tell you what the dimensions are and whatever. So I chose this one, and that one was in stock at the time. Standalone capacitors, what is this? Standalone capacitors, I chose this. It is a 8 millimeter and lead spacing 2.5 millimeters. So if we go here, is a through hole radial, how was it again, 8 millimeter and 2.5, 8 millimeter radial 2.5. So we can set this, and this is the same. Axial through hole 8 millimeter. Where is it? Not this. Okay, back to the footprints. I had to stop because I got confused. So C7 is a radial tantalum capacitor, 8 millimeter, 2.5% spacing as is specified here. Okay, so the same with the 10 microfarad tantalum capacitor. It's not SMD, it's radial tantalum 8 2.5. This one here, that's my problem. Let's save it. This is what I forgot. It's gonna be this capacitor 0.1 microfarad, 400 volt. Place it here, and we go back to this and to assign this capacitor 5 millimeters, 2.5 should be okay. Come on. Hold this capacitor. Now 560. Again, we have to go to DG find our capacitors, whatever capacitors you want, aluminum electrolytic capacitors. First is through hole and in stock. Apply. Let's say that you chose 560 and 35 volt is more than enough. 50 volt, whatever you want to choose. So let's say you chose this one, whatever it is. Vort, very nice. So it's 18 millimeters and lead spacing 7.5. So 18 millimeters and lead spacing 8.5. So radial 18 millimeters 7.5. That's it. And 18 millimeters 7.5 again. 470. It cannot be more than 5. So clear the capacitance. 470. Let's find the Part.1 again. So it is 10 millimeters, 5 millimeters lead spacing, 10 millimeters and 5, 10 millimeters and 5. So we have all our footprints assigned. This the terminal blocks are from DigiKey library, and this one that I chose and purchased, and the bridge is standardized. And of course, when we set the diode 1 November 407, it came up immediately. So all our footprints assigned, apply, save schematic and continue. So we have all our footprints assigned, and then we can go to File, Export, Netlist, KiCAD Netlist, Export Netlist. We'll save it the same folder as test. Save, and now we can go to PCB editor. You can grab here. At this point it says upgrade PCB. Where is it? Sorry. Create. We can go to File, Import, Netlist, Netlist, File. Where is it? Test.net. Open. It says update PCB. And this is all our components. So now that we are on our PCB editor, let's starting to build our PCB. This is where you're gonna spend most of your time. Try to arrange this to make your PCB the smallest one you can make. You can start with a predefined size if you know exactly what I did. I spent quite a lot of time here making the PCB smaller and smaller and smaller, trying rearranging it again and again and again and again until you get the smallest size you can get, and of course you can work. So make sure that your grid is a small one so you can work. And how I went around, I went to edge cuts. This is where the PCB is designed, and I draw a rectangle which was 82 millimeters long and 60 millimeters wide. Come on. Okay, I have my PCB ready. Then I'm going to at the fill zone. We need to fill it with copper so we can start building it. So go to this corner, and no, that's cuts here on the front copper. Gonna be earth, okay, and I'm filling it with so I have my filled PCB. Now I defined it, and then now I can go and start. So this is J1, this is the connector for the, before I do this, I can move my 4 holes to the 4 corners. What is this? H3. Put the H3 here. We can align them later. So I have 4 corners, then I get my terminal connector and put it here. Then I will bring my bridge, rotate it, so it will sit here. I forgot my C1 capacitor, which is first. Now I'm looking on my other schematic, and now I'm putting everything as I made my my PCB, but it's not that easy. As I said, you have to go through this whole process many times until you get exactly what you need. So we have C3, and then we have C4, which is, need to rotate it that way. And we have our heatsink. Let's put it here. We have our voltage regulator. We have a diode. Put it here. We have a capacitor. Output capacitor 1, output capacitor 2. By pressing R, you rotate the component. Have a smoothing cap, and finally our output connector. So we have a basic sketch. As I said, you will go through a lot with this, and of course you can make it a bit smaller, but I want it sorry, I want it to be quite easy for me to work. So now that we have all our components placed where we want to, we can start placing tracks. So I use the 1mm track to have big supply. So from here I need to go to D3. This is the plus side. I need to go to D3 from the minus here and to D2. Let's make it a big. So it's not crossed. That's the output of the bridge to C2, and from C2 to C3 as a parallel. This NORMET class from this capacitor to go to the standalone capacitor. So in this case we have to go back to let's save this. Let's go back and well, there's no problem. There is a problem here. That's the problem. That's the problem. So now we have saved it. We need to save the net list again. Export net list. Replace, and then go back to the PCB editor and go and update PCB from schematic. Update PCB, close, and now we have the net class going from C3 capacitor to the standalone capacitor. So now we can connect it. Now we have one problem. There is one trace coming from the output of the voltage regulator to the output capacitors, and we have one trace that goes from the regulator to the input of the capacitor. The easiest way to trick this is to put the trace on the back copper plane. So I will put this on the back plane and then switch on the front plane to make the connection here. Up, nope, why? Escape, I don't need, I need 1 millimeter. But I have a problem here, why? Let's move the diode a bit. Make more room. And we go back to, nope. This one, and back to front copper. That's a problem. Okay, I'm back. I found out what the problem was. This symbol was pressed for some reason. It says that, come on, sorry. It says, when routing from an existing track, use its width instead of the current width setting. So if you press this, then the whole width is 1.1 millimeters, so then it will make your track like this. So I deselected this, and now of course I can make a 1 millimeter track here and 1 millimeter track there. And the PCB is almost ready. One thing remains. Click, you press B, and it's filled with copper. All the earth is filled automatically, and this is a 2-layer PCB. That's why we could put the track beneath, so they don't intersect. And basically this is a PCB. Of course, we can go on the front silk now and start putting texts. This is there on the front silk. This we can move. This we can move a bit. Come on. Make the grid a bit smaller so we can move everything where we want to move them. Come on. J1 and put it there, and J1. You can put J1 here. Put C5, we rotate it and put it here. We can take C6, rotate it and put it here. You can write on the front silk anything you want. I put text here, and actually what I do is it's easier. I will copy this, Command C, and then I will make the text, paste it, and put it there. So on the front circle it will show so here come by, but this is just to make your PCB looks nicer. It's not a requirement. Wherever you want to put them, you understand. And this is our PCB. You save it, of course, and then we go to fabrication outputs. You output the Gerbers and the drill files for the holes. Something I forgot to say. You can come here and change the properties of the holes. One thing that can do is make it bigger. Of course, you cannot make it too big. Okay, 3.7 bigger pads would mean greater dissipation for the heat, and of course the hole size must be 1.4 millimeter is exactly very strict fitting in, so you can make it 1.5 for this kind of bridge rectifier. So bigger pads will mean bigger, greater heat dissipation if you don't want to use a heat sink on the bridge rectifier. Size is 3. And 3 because it's a square, and 1.5 hole. Okay, come here again, fill it again. You can change the sizes of all the pads if you want to, and finally you can run the RC check, and it will tell you all the errors that we have. So we have track has unconnected end. Where is the track with the unconnected end? And clearance violation, a class default clearance, actual, we have a clearance fault. Where is that? Through hole pad earth of D1. Here. So we make this pad bigger, and now there is not enough clearance with the track. So we can go and delete the track, and we can come here again and come on and make it like this. Go back to our thing and fill it. Now let's run a DRC again. So we corrected this one. Cortilabs overlap. This one it doesn't matter, but we have an unconnected and .NET class C5. .NET class C5. So back on the problem, guys. I just moved the regulator, and behind it there is a track from before when I was trying, and the the traces were too small. I drew a track there, and of course the schematic takes it as an error. So I had to delete this track. This is what you will have to do sometimes, guys. Okay, so placing it back where it was on the heatsink. Yes, good. Let's fill it up with copper again. Now make the connections. Fill it up again. And let's run DRC now. And magically the errors was. This courtyard's overlap doesn't really matter. There's no consequences because I placed the you have to place the voltage regulator exactly even more, so it cannot be attached to the holes will be on the correct side, so you can attach it on the heatsink. So basically this is our PCB. As I said, you can go fabrication output. You will export a Gerber file, you will export a drill file, you will make it as a zip file, and then send it to your favorite PCB manufacturer, and it will come back with your PCBs. Now, on the next thing, we will pick it up when we actually gonna make the power supply. Thanks for watching so far.